Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So welcome to the third lecture of the dynamic programming playlist. It's a wonderful question. Frog jump. So just to make sure you have watched the previous couple of lectures before attending this one, because I have a perfect flow which I will continue. So if you're just watching this lecture 3, suddenly you might feel alienated. So please watch out the previous couple of lectures. So what is the problem statement? So there is a frog on the first step of a n stairs long staircase. So the frog wants to reach the nth stair. Height I is the height of the I plus 1th stair. So the array is given in terms of zero based indexing, right? So the energy lost in the jump is given by height I minus 1 and height j minus 1. So basically the frog can jump from the ith stair to the jth stair, and the energy will be height of I minus 1 minus height of j minus 1. In the frog, if the frog is in the ith staircase, he can jump either to I plus 1th stair or to I plus 2th stair. Basically, he can take a jump to the plus 1 index or to the plus 2 index. Your task is to find the minimum total energy used by the frog to reach the first stair to the nth stair. Okay, so that is what the question states. So for an example, I'll just take the first example 10, 20, 30 and 10. Okay, and I'll try to explain you this. Let's take the first example, which is 10, 20, 30 and 10. So basically there's a frog. Now if I consider this as 0, 1, 2, 3, the frog wants to reach from 0 to 3. I have converted the problem into zero based indexing. So even if n is 4, it's ideally the question was from 1 to 4, but I have converted it into zero based indexing. Okay, so if the frog starts from here and he can only jump one or two places, what is the minimum energy that he will require? Okay, so for example, if the frog is here, and the frog says that okay, I will jump from here to here, then the energy that he will require is 10. Okay, and then he decides that he'll jump from here to here, then the energy again required will be 10. It's a difference of them, absolute difference of them. Okay, so if after that he decides that he'll jump from here to here, that's again the absolute difference, which is 20. So this path will give him 40. The energy that he will take will be 40. Let's try out some other paths. What if I decide I will jump from here to here, which will take me 10? What if I decide I'll jump from here to here? So that again takes me plus 10, correct? So this path gives me 20, which is definitely better than the previous one. What if I decide I'll take this a couple jump, because I cannot jump more than a couple of steps. So this will be 20, and then I'll decide I'll jump one step. So that will be plus 20 again. This is again 40. So if you see, I've tried out one possible way, two possible way, three possible way, and the minimum that I encounter is 20. And you have to tell me what is the minimal energy that you can take, and that is what the question is. Now, can I say this? That this question again gives me an idea that you are trying all ways. So if you remember the previous lecture, I told you, if you are trying all possible ways, then it's a recursion, right? And then you can either count all ways or you can find the best. So can I say over here, you're trying all possible ways, way number 1, way number 2, way number 3, and you're taking the best possible, and that's 20. Why will a greedy solution not work over here? That might be a question that comes to your head. So that's the first thing that I will be talking about, why a greedy solution doesn't works. Let's understand that. Then after that we'll think why we need to try all possible ways and need to take the best way out. So when I say greedy, that means you are standing from 10. So from 10 you can go to 20 or go to 30. So you saw that if you jump till 20, that's the minimal, so you jumped. And from 20 you could have either jumped to 30 or to 10. Both are taking 10, so you can jump anywhere, so you jump this is greedy. Basically, when you are moving, you try to jump the minimal possible jumps possible, whichever takes minimal energy, you try to jump that. But why a greedy solution doesn't works, let's check that out. Now when I say a greedy solution doesn't works out, let's check this test case. So if the frog was here, greedily from here he will try to move here, because in moving here it will take him 30, it will take him 20. The greedy option will be to move to 10. So let's greedily move to 10, which will cost him 20. Okay. Now again, from here he can move here, which is 50, or he can move here, which is 0. So greedily he will move to 0. So let's move to the 0. This will take him 0 energy. Again, from here greedily he can move here, which will cost him 40, or this will cost him 50. So greedily he will take the 40 wala stuff. So he will move from here to here, which will be again 40. So in total the costing will be 60. Yes, in total the costing will be 60. Now what if I try some other way? Let's try that out. If the frog is here and he decides he will be going till 60, that will cost him 30 buck, right? And if he decides after that he'll go to 60 again, that will cost him 0. And after that he decides he'll go 50, that will cost him 10. So a total of 40 will be the costing. A total of 40 will be the costing. So we did realize the greedy way did not give you the correct path, because you started greedily but you lost out probably somewhere, right? So that's why it's better if you try all possible ways, because sometimes it will happen that initially you took the better way but you lost out on something significant, like this 60 to 60 would have been 0. You lost out in future. So in such cases greedy doesn't works and you have to try recursion. Now when I say recursion, boils down to the second lecture. What is over here? Recursion is try all possible ways. So you have to try all possible ways. Okay. So in order to try all possible ways, you have to write recursion. Correct? Over here, they're asking you which path did take the minimum energy. So you have to find the path with the minimum energy. Correct? And do you remember the previous lecture? What was the step number 1? Express the problem in terms of index. Do all stuffs on that index. Remember this. To write recursion, do all stuffs on that index. Step 3. Over here they're asking you to find the minimum energy that you took. So take the minimal of all stuffs. Take the minimal of all stuffs. This is how you write recursion. Okay. So can I say I'm wanting to reach the index n minus 1. I'm assuming 0 based indexing. So I'm wanting to reach the index n minus 1. So what do I want? What does f of n minus 1 signify? Minimum energy required to reach n minus 1 from 0 index. That is what the recursion will signify. Can I express the recursion in terms of index? That's my first step. I'll be like, yes, you can. How? There are array indexes. Till n minus 1. So I'll consider every array index as an index. So, okay, that's fine. So I can be like, okay, that's absolutely fine. So let's do it. So can I say, what will be f of 0? Like common sense. What will be the costing in order to reach from 0 to 0? That's going to be 0. Because f of n minus 1 was stating the costing from n minus 1 to 0. So in order to reach 0 to 0, the costing will be 0. So I know one thing for sure, that the costing for this guy will be 0 no matter what you do. Now, so we have figured out what is the index. That will be the array index. Next thing is, do all stuffs on that index. Yes, do all stuffs on that index. Now what is the frog allowed to do? The frog is allowed to either jump +1 or to either jump +2. So why don't you do that? Do all stuffs on that index. Please do it. So what you will do is, you'll say, okay, I will do all stuffs on that index. So if I do a single jump, like I can say it as the left recursion. So the single jump will say f of index minus 1. I'm doing this. But if I'm jumping, yes, the question arises, if I'm jumping from an index to an index minus 1, what is the energy that is being consumed? I know in order to jump from index to index minus 1, the energy consumed is array of index minus array of index minus 1. That is what the energy is consumed. Can I say this is what the energy will be consumed to jump from index to index minus 1? And then I can ask the recursion, hey recursion, I have reached index minus 1. Now it's your job to tell me from index -1 to 0 how much it will cost you. Recursion will do the job. I'll ask the recursion to tell what will be the costing from index -1 to 0, because I know the costing from index to index -1. I've taken that. So that's what I'll do. First step done. Now can I say the right recursion will be very simple? It will be, if I take couple of jumps, the costing this time will be a of index minus a of index minus 2. Absolutely makes sense. So I've done all the stuffs, but I need to be slightly careful. Can I do an index -2 always? The answer to that is yes, you can do it if it is not the first index, because if you are standing at the first index, you cannot jump 2, because that will take you to -1. You cannot jump 2. So you need to write a case like this. If index is greater than 1, then only I can take the right jump. Otherwise I cannot. Like, makes sense, because if you add the first index, you'll not be able to take the right jump. So that is absolutely making sense. So I'm like, okay, fine, that's fine. Now, what's the next stuff? Take the minimal, because the question stated minimum energy. Had the question stated maximum energy, you would have done it. Had the question stated something else, you would have done it according. But in this, the question stated, find the minimum energy. So there is a way in which you jumped from index to index -1. There's a way in which you jump from index to index -2 and ask the recursion to find out the remaining answer. So can I say you need the minimal answer? So you're going to return the minimal of left comma right. That's how you can write the recurrence. As I told you, follow 3 techniques. You'll be able to write any recurrence relationships. Yes. Now you have written the recurrence relationship. That is absolutely perfect. So we have understood the recurrence relationship. Now it's time to see if there are overlapping subproblems and how is this recursion actually working, right? So we know we are at f of 5, because if I write down the indexes, it's like 0, 1, 2, 3, 4, 5. So we know we are at f of 5. Now at f of 5, where can we go? We know that either we can take a jump to f of 4, or either we can take a jump to f of 3. That's definitely known to us. So I can be like, okay, if I'm at f of 5 and there's this recursion call, then the left recursion will be like, okay, f of 4 plus absolute of whatever height there is. So what is the height? 60 minus 50. There's this height of absolute 10. And then there's the recursion of right, which is f of 3 plus again an height difference of these couple of guys, which is 3 and 5. 10 minus 50 is 40. So you can be like absolute of 40. Now at first this recursion will go, come back, and then this will go and come back. Then you'll return the minimum of these. Alright, this is how the recursion is actually working. So that's how I'm drawing the recursion tree. So f of 4 will say f of 3 and f of 2. F of 3 will say f of 2 and f of 1. F of 2 will say f of 1 and f of 0. Understood? Right? So do you observe overlapping subproblems? At least I'm able to do it. By the way, f of 1 will go to f of 0 as well. I'm able to do it. So if I mark the overlapping subproblems, there is one. First one. Another one. So I have figured out if f of 3 answer, if f of 3's answer I'm figuring out, then f of 3's answer, why will I again figure out? So there are overlapping subproblems. So if there are overlapping subproblems, can I say the answer to those subproblems will be similar? Thereby I can apply memoization to this particular recursion. Got it? So I'm understanding that, okay, I can definitely apply memoization. So you can easily apply memoization, but just in case to complete the recursion tree, I'll quickly draw it. So in order to reach 0, I'll take 0 amount, correct? So f of 1, what it would have done ideally. In f of 1 was this recursion. So f of 1 went, and there was a left recursion call of f of 0 plus the jump from 1 to 0. So absolute of something, a jump from 1 to 0. So absolute of something, let's see. 1 to 0 will cost you 20. So you can add a 20. What about the right recursion? Can I say, since we are standing at the first index, there will be no right recursion, because you cannot jump couple of index. So I can say right is probably some bigger value. Now f of 0 will return you 0 for sure. This will return you 0. So the left took 20 and the right took 20. So what will you return? You return the minimum of both of them, which is 20 comma, Let's assume this to be some int max. So it's 20 what you return as f of 1. Again, makes sense, because if you're standing at f of 1, what is the cost that you'll take from 1 to 0? That's one way. There's only one way, which is 20. So that is what we have stored. Cool. So I have drawn this particular recursion. Nice. Now we are at f of 2. So f of 2 would have called the left recursion as f of 1 plus a jump from 2 to 1 plus a jump from 2 to 1, which will cost him 50. So that costed him 50. And there will be a right jump, which will be directly to f of 0. Now there will be a jump from 2 to 0, which will cost him 30. So there will be a 30. Now you remember f of 1, this had a value of 20. So it will return with a 20. So this guy gave him 20. So 20 plus 50 will give him 70. F of 0 will be how much? 0. So 0 plus 30 gives him 30. Which one will f of 2 give? The minimum. So it will return 30. So f of 2 got 30. Perfect. So again, makes sense, because if I logically explain you, let me erase this. If I logically give you an explanation, will this make sense? Yes, this will make sense, because if I'm standing at f of 2, yes, if I'm standing at f of 2, there are a couple of ways. One is this, which will cost him 20 plus 50, which is 70. Or the other one is this, which is 30. So 30 is what you have got, right? Now again, similarly f of 3. When you're at f of 3, understand, there is a left call of f of 2 plus the absolute difference, which is from 3 to 2. So if you're doing from 3 to 2, it's 50. So you can just take a plus 50. So what is f of 2? It has returned you as 30. Correct? What's the right jump? The right jump is about f of 1 plus what? Now will you f of 1, so from 1 to 3 will be 0. 1 to 3 will be 0. So plus 0. Now will you go and do the recursion call of f of 1? Will you go and do again f of 0? F of 1 is already computed, you see. So it's overlapping sub problem. You can directly take the value from the DP array as 20. This gives you 20. This gives you 80. Which one will you take? 20 obviously, yeah. So f of 3 becomes 20. Perfect. So remember, I'm storing the values of f of 3, f of 2, f of 1 in probably some DP array, as you have seen in my lecture 1. Next, you're at f of 4. So if I'm at f of 4, what is that doing? It's again calling f of 3 plus absolute of 3 to 4 will be 50. So 50. And it's calling f of 2 plus 4 to 2 will be 0. So I can do 0. What's f of 3? If I write what's f of 3? 20. What's f of 2? 30. So 20 plus 50 is 70. This is 30. Which one will you take? 30. Again, an overlapping sub problem ignored. You did not, f of 2 will not go deep into recursion, because the moment you call f of 2, it will directly get the value 30 and return 30. So you got the minimum as 30. So f of 4 becomes 30. Perfect. Next step is this particular step, f of 3. So when I'm at f of 5, what's happening? I'm saying, okay, I can definitely go to f of 4 plus absolute of jumping from 4 to 5, which is 10. So let's take 10. Similarly, if I am jumping from 5 to 3, can I say it's 40? Yes. So plus 40 of f of 3. Now carefully observe, f of 4 is already 30, f of 3 is already 20. 30 plus 10 gives you 40, 20 plus 40 gives you 60. Which one will you take, 40 or 60? Definitely 40. So this value is 40. Thereby this recursion is also solved. So did you observe something? There were multiple sub problems that I ended up solving repeatedly, overlapping sub problems, as I said. So this is how generally recursion tends to work. It goes on, because if a problem has been solved, if you already know what's the summation from 0 to 3, why do you want to recompute it again? Just reuse it. That's what I've done, and I've got the answer as 40, which was indeed the answer. This is how the recursion tree works and how you get the minimal possible way. Generally, if you draw this recursion tree by yourself, you'll understand much more. But in general, if you can remember these three stuffs, three lines, explain the problem in terms of index, do all stuffs on that index, take the minimum of all those stuffs, and then write the recurrence. Now, once you've written the recurrence, how do you convert a recurrence into a dynamic programming solution? That's the next question. How do you convert a recurrence into a DP? So that's when you say memoization. Okay. So trick to apply memoization. Look at the parameters changing. Yes. Look at the parameters changing. Like which parameters are changing. Just look at them. You'll be like, Striver, there is only one parameter changing. Which is the one parameter? Let's come back. It's index. What is the maximum value of index? Let's look at the recursion tree. 5. So you'll require a 6 size array, because in a 6 size array, there'll be index 5. So you can definitely create a DP size of 6 over here, which is indirectly DP of n plus 1. Remember 3 steps. Step 1 is this: declare an array of size n plus 1. Step 2, before returning, add it up. DP of index. Before returning, add it up. Store it and return. So this is step 2. What's step 3? Whenever you call an index, yes, whenever you call a recursion, check if it has been previously computed or not. If DP of index has been previously computed, no need to solve it again. Return DP of index. Done. Line number 3 converts a recursion to a memoization. So I've converted a DP solution converted a recursion solution into a dynamic programming. And if I talk about the time complexity, what will be it? 1 step, 2 step, 3 step, 4 step, 5 steps. These steps are constant because these subproblems are not solved. So these steps are constant. 5 steps or n steps. So I can say the time complexity to be big O of n because there are n steps. I can say there is recursion stack space of big O of 1 and an array size of big O of n used. This is how the recursion will look alike. So it's now time to code it and probably submit it, and after that we can optimize this into tabulation, and after that probably into space optimization. Okay, so in the code you are basically given n and you're given the heights. So I know I have to write a recursion solution, so probably I have to term that in terms of index, and let's carry the height as well. But the Java people, you can easily code it because I've explained the pseudocode while explaining, so should not be a big issue for Java people as well. So I'll take int function. Now I know the edge cases. If index reaches 0, I know the answer will be 0. And I know there will be a left recursion call. And I know there will be a right recursion call. But we know one thing, the right recursion call will always not happen. So probably we can initially store that as int max because this is not going to happen always. If index is greater than 1, then we can have the right as f of index minus 2 and pass on the heights. And then a plus of absolute of heights. Like you can just heights of index minus heights of index minus 2. That's something which you can definitely do. And over here what you can do is the same stuff, just make sure you copy paste, and instead of index minus 2, do all the stuffs, and yeah, that's how you do it. And at the end of the day, what do? You return minimum of left comma right, correct? Now the question is very simple. So you can probably say return f of n minus 1 because that's the last index, and you can do an heights. So if I run this, will this run? Let's check it out. Okay, so it says, okay, so int max it is not taking, so probably we have to use hash include bits std c++.h. Generally it is added over there. Not sure why they have not added it, but not an issue. Let's quickly run this off. So if I run it, you can see. So if I run it, you can see the first 3 test cases are running fine, and then there's a time limit exceeded because it's the simple recursive solution. So how do you convert this into a DP? Create a DP array of size n plus 1 because that's the maximum. Initialize that with -1. Now pass a DP. Over here, just make sure you have a vector of int, and you can just create a dp by reference. Make sure always carry the dp. That's the next step. Done. So step 1 of initialization and carrying on the parameters is done. What's the next step? Step 2 is storing the answer before returning for the subproblem f. Done. What's the next step? If the answer has come across, just check this and return dp of index, right? So if I just do these changes and if I now run, bingo, works fine, all the test cases. If I submit them, you will see it's absolutely correct. So this is how you can do the memoization stuff very, very easily. So in the first lecture I told you after memoization, it's very important to understand how do we do the tabulation one, and after that we will do the space optimization. What is memoization? Top down. Why? Let's understand. So in the recursion, if you observe, what did you do? You had a top portion, but first the down answers, like you went from top to down, correct? What is tabulation? It's the exact opposite. Yes, I repeat, it's the exact opposite. Bottom up. Okay. That means you'll start from the bottom and you'll go up. So always look at the recursion tree. Always look at the recursion tree. What's at the bottom? Yes. So you'll go up and then you'll fill it. You'll take 0, you'll fill 1, then you'll fill 2, then you'll fill 3, then you'll fill 4, you'll fill 5. You'll go from the bottom to the up. So that's tabulation. Understood? Now, what did I tell you in tabulation? What's the first step? Step 1 is to see in memoization how much DP array did you use. We know we used a DP array of size n plus 1. So just without thinking anything, you can initialize that. Okay, so without thinking anything, you can initialize that. By the way, it will be n. Like even if you initialize n, it will work because we have used a 0-based indexing. So make sure everything is initialized with -1, or you can initialize that with 0, doesn't matter over here. So first thing is done. What's the next step? Look for the base case, because in recursion it is top down. Over here it's down top, like bottom up. So what's the base case? Let's look at it. The base case states index equal to 0, return 0. Index equal to 0. Index equal to 0. So whatever is that, you'll write that. dp of 0 is equal to 0. Just write it. After that, just look at the recursion state. These lines, when will it be executed? I can be like, it will be executed at 1, 2, 3, 4, and so on till n-1th index. Makes sense, because the worst call that I'll make will be n-1. So it will be executed for sure. I'll be like, yes. So please write it. I equal to 1 till n-1. Run a for loop. Perfect. What's the next step? Just go and look at the recursion. What am I doing? What's the stuff done on the index? Yes. Replace this with dp and write it. So the first step is very simple. I can say if I take first step, it will be dp of index -1 plus absolute of array of index minus array of index -1. Simple. I can say second step will only implicate if I is greater than 1. Remember, super simple. Second step will only implement if that's true. So dp of index -2 plus absolute of a of index minus a of index -2. As simple as it gets. And what do you store? Store it. dp of index will be minimum of dp of index dp of first step and second step. As simple as it can get. And if you write this, it's definitely going to work wonders. So I'll try to show you over here. Like I'll just erase this. And over here, if I just write the same thing, like you'll see over here. If I try to write the same thing, like I'll write dp of 0 to be 0 for I and I equal to 1, I lesser than n, I plus plus. Okay. And I can write int first step will be very simple, dp of I minus 1 plus absolute of heights I minus heights of I minus 1, right? And what about the second step? I can say the second step will be very simple. I can initially keep it as int max, correct? And what I can say is second step will only be implicated if index is greater than 1, and the second step will be nothing but dp of I minus 2 plus absolute of heights of I minus heights of I minus 2, as simple as it gets. And the dp of I will be minimum of dp of I minus 1, sorry, minimum of first step comma second step. And what do you need to return? You need to return the answer will always be stored at the last index, and thereby if I just take this off now, and now if I try to run, you see it's running, and if I try to submit, works fine. So we can convert this into tabulation so easily by a like a recursion can be converted into a tabulation. Now the question arises, can we reduce the space? Because over here we are definitely reducing the stack space that we used over here. This is reduced, but there's still a big of n being used, because as I can see we are still using a dp of n array, and the time complexity cannot be reduced. But can I omit this? Let's see, can we omit this? I did tell you one thing. Anytime there is something like index minus 1, index minus 2, there can always be a space optimization. Take this as a thumb rule. There will always be a space optimization if there is something like index minus 1 and index minus 2. Always. These states can be. Now let me tell you something. Assume you are at index 0, 1, 2, 3, 4 and so on till n minus 1. Okay. Initially, assume you are over here and this is nothing but dp of I. And you're saying this as dp of I minus 1 and you're saying this as dp of I minus 2. You're saying correct. In the next step, whenever I will increase, can I say that I will go over here and this will be dp of I, this will be dp of I minus 1, this will be dp of I minus 2. Indeed I can. There's no doubt I cannot. In the next step, can I say this will be dp of I, this will be dp of I minus 1, this will be dp of I minus 2. There's no doubt. So do you observe a pattern? The guy who was dp of I minus 1 for this particular I, in the next step, when the I increases to the next index 3, the guy who was I minus 1, that means he was the previous. He'll become the second previous of the next. He'll become the second previous of the next. Makes sense? So he'll become this. So can I say dp of I minus 2 will become this, right? So do you need to carry an array? Can't I do this using couple of variables? Like think, can't you do this using couple of variables? The answer to that will be yeah, I think we can, because what we require at any particular instance I is the previous guy and the second previous guy. I don't need anything more. Why the hell do I need to declare a dp array? I don't need anything else. Thereby I can say, okay, so that makes sense. Let's assume I do it this way. This is cur I say this is previous I, and I say this is previous to I, instead of storing them into an array. In the next step, I know this will become cur I know the cur I will become previous I know the previous I will become previous to I. So can I just use couple of variables where I say previous to I for the next step, whenever you have done all the stuffs, the previous I will become the previous to I, because whoever is previous will become second previous for the next step. And whoever is the current guy, like whatever is the value of dp of I, that will become the previous for the next step. So if you just keep on doing this, you'll no more require anything. So can I say this? Instead of dp of 0, can I carry a previous equal to 0? Makes sense, I can. And can I carry a previous 2 equal to probably 0 as well? Because for the first, you'll require dp of index minus 1, which I can represent as previous now, correct? And this I can represent as previous 2, because that is what we recommend. And after that, can I say In the next step, the previous 2 will be previous, and the previous will be nothing but cur I, and this guy will be cur I. Make sense? Make sense? And what will be the answer at the end? Whenever you exceed, I will go beyond n minus 1, and whenever this for loop ends, the value of I will be n. Yes, the value of I will be over here, and for this guy, previous will be at n minus 1, and you always require the answer of n minus 1. So you can say whatever is the answer for previous will be your answer. So you can easily print the answer as previous. So if you do this, you will be able to get your space optimized, and you'll no more be requiring a DP array. So if I try to write this in the code, probably I'll delete this, and I can keep a previous equal to 0. I can keep a previous 2 as well as 0, and I can just omit this to previous, and I can just omit this to previous 2, and I can be like this to be cur I, and I can say the previous 2 will become previous now, and the previous guy will be, for the next step, will be cur I. Correct. And at the end of the day, instead of dp of n, because I will be at n minus 1, so I can definitely return something as previous. So if I run this, here it works. Let's submit. It is working fine. So we have done a space optimization. Yes, we have done a space optimization. So this is how this problem can be easily solved. So this is how I can space optimize it. I hope you have understood the space optimization. Now there's a follow-up to this wonderful problem. Okay. Now this question stated you can jump to I plus 1 and you can jump to I plus 2. That's the maximum that you put. Now the follow-up states there can be k jumps. Yes, the follow-up states that there can be k jumps. Now instead of I plus 1, you can jump to I plus 1, I plus 2, I plus 3 till I plus k. That's what I'm saying. So if I change the question to this, can you solve this problem? Now I'll give you this as an homework. Okay, so take this question as an homework. I want you to do k jumps. If you are using k jumps, then probably you cannot use space optimization, because then there will not be couple of stuff. There'll be k previous elements that you have to carry. You will not be able to use stuff that I told you. But yeah, the stuff that I gave you was, the follow-up is very simple. Try to do it using k jumps. I will expect the codes in the comment section, and I'll be discussing this problem right before starting the lecture 4. Right before starting the lecture 4, I'll definitely be discussing this problem k jumps, where I'll tell you how to change this problem slightly, and you'll be able to do this problem for k jumps. So guys, if you have watched this video till now, and if you've understood everything, you know what to do. This is what I expect. Even if you're very lazy, please comment US. US means understood, and this is something which you should always do. You're watching these videos because it takes a hell lot of effort to make these kind of videos. And yes, if you're new to this channel, please do consider subscribing, and please do share this channel among your college mates, friends, wherever you can. And if you haven't checked out our SD sheet yet, oh man, what are you doing? There's an SD sheet link in the description. Go and check it out. That's the ultimate resource for placements, man. And yeah, with this, let's wrap up this video and probably meet in the next one tomorrow. Bye bye, take care.
Whenever your heart is broken, don't ever forget your golden